oh, sorry, wait. Okay, regarding a Whipple formula. Okay, so before I start here, I list the three articles by Boykers, Roberts, and Rogers, Viegas, and Long. I think they give a nice introduction about the hypergeometric functions, hypergeometric motifs, and also some examples and open questions related to this talk and my previous talk on supercongruence. So, and yeah, some of the background in my talk are discussed in previous talk by Boykers and Rogers, Viegas, and also my talk. So yeah, I could like to apologize that if you already see many examples and the definition before. So okay, so apology number one, the definition of hypergeometric functions. Okay, so classical hypergeometric functions are defined as this formal power series, and it's a solution of the answer order differential equation. This differential equation around the singularity is equal to 0. Yeah, and for this differential equation, it's a function equation with three singularities, 0, 1, and infinity. So for this function itself, the coefficients here are defined in terms of the Pohemer symbol or the rising factorial, which we can also written as gamma quotient like this. So take n equal to 2, the 2f1, for example. So for 2f1 function, it satisfies second order hypergeometric differential equation with singularity 0, 1, and infinity. So, so the monotomic group is a triangle group. Yeah. So this gives us a application that if we consider module forms on arithmetic triangle groups, then they can be expressed in terms of hypergeometric functions. Okay, and another example is that if we consider the integral representative of the 2f1 function, then they can be viewed as a series of centered algebraic curves. For example, the Legendre curves we have seen in previous talk. So let's look at the example on module form part first, then I will go back to the Legendre curve. So first of all, if we consider lambda to be the classical module lambda function on gamma 2, the principal congruence subgroup gamma 2, and it is a triangle group with exactly 3 cusps. So now if we, okay, so so the square of this 2f1 function is then a way2 module form, which is the same as the fourth power of Jacobi theta 3 functions. Okay, and also in some special cases, the square of 2f1 function is equal to a 3f2 hypergeometric function. So for example, if we apply a suitable quadratic formula and the constant formula, so we get a 3f2 function like this. Yeah, and if we let T to be a module function on gamma 02, again, which is a triangle group, it has one initial point of order 2 and 2 cusps. So this 3f2 function is a way2 module form, and it's the fourth power of the Jacobi theta 4 function. And if you are more familiar with the King eta functions, this is its expression. So another example that you may aware is the Riemann type 1/pi series, which is also can be obtained by the hypergeometric function. For example, usually you will see the formal power series like this form. Yeah, and this, for example, for this one, it can be written as this 4f3 function by, okay, here, if you look at the red column here, the quotient of the rising factorial coming from the 5/4 and 1/4 exactly the 4K path right here. Okay, so okay, so for this case again, it can be written in terms of a 3f2 function and its derivative. So for this part is coming from 1 times these guys, and for 4K times this guy, they are related to these derivatives. Yeah. So again, if we let the t be this module function on gamma 02, then this 4f3 can be written as the theta 4 and the t function and their derivatives. So this is a special, this is an example of the so-called Ramanujan-Sato series. And for the Ramanujan 1 over pi formula, so in this case, it is reduced to compute the spatial value of these module forms. Okay, so now Legendre elliptic curves. So, okay, if we consider the period of the Legendre elliptic curves, so we integrate the differential one form of the elliptic curves along the path 0, 1. So this actually the integral representative of the 2f1 function times the transcendental number pi here. Okay, so if we consider the trace of covariance of the elliptic curves, then okay, they are given by the caret sign here. So to save space, I use phi to denote the quadratic caret, which is the Legendre symbol in this case. So anyway, if we do point counting, we get over fp, so we get the p path 1 plus some arrow turns here. So this arrow turn, the AP value I define here is the trace of covariance of the Galois representation. And also from the modularity theorem, we know that for a fixed lambda, the AP value gives us a Fourier expansion of a way-to cast form. And also, if we look at the PID version of this identity, so the right-hand side is congruent to this finite sum. So, and this is the partial sum of the original 2f1 function. So this gives us a congruence relation between the AP value and the truncated 2f1 function. Truncated at least p minus 1 over 2. Okay. So another example, that's the K3 surface example. If we consider smooth model of this surface defined by this equation, so actually algorithms show that this one is this curve is, sorry, this surface is modular. So and the corresponding Hecke eigenform is this V3 eigenform. Yeah. And he also showed the supercongruence to relate this 3f truncated 3f2 and the coefficients of this V3 eigenform. As an Archimedean version of this supercongruence, actually we can write the 3f2 value in terms of a period of this V3 module form, which is written as the spatial value, L value of this V3 module form. Yeah. For another example from our Calabi-Yau threefold case, again, if we consider the threefold whose Picard-Whose differential equation is related to this 4f3 function, so we know that from our previous talks that we know this is modular, and the corresponding, the corresponding Hecke eigenform is this wave 4 eigenform. And similarly, Legendre showed that we can write the 4f3 values in terms of the spatial error value of this wave 4 eigenform. Yeah. So from this example, we see that if we have a given hypergeometric functions, so yeah, like the Legendre elliptic curve case, we can consider the corresponding Galois representations. And from the the Galois representations of the binary variety or their error functions. And also we can talk about the modularity of the Galois representations and the PAD version like supercongruence. And also, as we see in this talk, like Laguerre's example, we can relate the hypergeometric values to the periods of the module forms. Yeah. Okay. So, but I want to point out that for given hypergeometric function, actually we have the corresponding hypergeometric Galois representation, which is given by cats through hypergeometric shifts and the rigidity. Yeah. So the question is that are those Galois representations are modular? So for example, and another thing is that can we find the corresponding module forms like classical module form, Hilbert module form, or legal module forms? Blah, blah, blah. Yeah. Okay. So in this talk, we will focus on the Galois representation part. And again, like last time, we will use the hypergeometric type of carrier sums to give us information on the Galois representations. Yeah, and also we will discuss the modularities of certain Galois representations. And as I showed in my example that some of the module forms can be expressed in terms of hypergeometric functions. So this gives us some ideas to relate hypergeometric evaluation to periods of module forms. So this also gives us some idea to identify the module form through the if the Galois representation are modular. Yeah, but of course we can look at the data and identify the corresponding module forms by looking at the base prime and also the sales result to identify the candidate of a module form. But this is kind of some idea how to relate this hypergeometric value to periods of module forms. Okay, so so for all of these, they are built from the so-called hypergeometric data. Okay, so what's a hypergeometric data? So anyway, hypergeometric data consists to multi-set alpha, beta, and the argument d. Anyway, it's from the hypergeometric function. We're collecting all the upper parameter, lower parameter, and the argument. But here we will require the AI BJ are not defined by integer, because we see in my previous example related to non-Randall-John-Sato series. For letter 4f3, actually we can express it in terms of 3f2 and its derivative. Okay. Okay, some notation or some definition. So the pair alpha beta is said to be self-dual if, okay, also column vector. If this set is congruent to this set for mod Z. For example, if we consider 1/3, 2/3, and 1/1 is self-dual, but 1/3, 2/3, and 1/2 is not self-dual. Okay. Because if we put 1/3 and 1 here, the minus 1/3 is congruent to 2/3, and minus 1 is again congruent to 1, but the second column should be 2/3 and 1/2. Okay, so it's not self-dual. Okay, and we said that the pair alpha beta is defined over Q if, okay, roughly speaking, if the set is closed under the multiplication multiple by all the numbers Z co-prime to the least common denominator of all the parameters AI BJ, then we say that this pair is defined over Q. Yeah. Again, the example 1/3, 2/3, and 1/2 is not defined over Q. but the second pair, coming from, so an example in our Calabi-Yau threefold case. So this one is self-dual and also defined over Q. Okay, so now we have a pair which is self-dual and defined over Q for hypergeometric data. Okay. So here, so a hypergeometric data is said to be self-dual if the pair alpha beta is self-dual and the Z is a real number. So, and in this talk, when I say a hypergeometric data is defined over Q if the pair is defined over Q and the argument is a rational number. So about this definition, roughly speaking, is that the corresponding Galois representation is that it's isomorphic to its complex conjugation if the data is self-dual. Okay. And for defined over Q, the representation is isomorphic to its Galois conjugation arising from the cyclotomic field of the nth root of unity. So this is kind of an idea why we define the self-dual and define the definition about the self-dual and the define over Q. Okay, so this is a hypergeometric data that I will talk about in this talk. So, okay, now the Whipple formula that in my title. Now, actually, this is a special form of the original Whipple formula. But yeah, in this case, first we consider the self-dual case. Okay, so here we have. Okay, anyways, for this special case, we have some parameters here, C and F. And also there is a number P here, but here we fix it to be a prime number. And CF are some rational numbers between 0 and 1. And now, so in this joint work, we are considering the corresponding hypergeometric Galois representations. And also we discussed the modularities about these Galois representations. Yeah, and also relate the hypergeometric value for this. For example, this is 7F6 to certain periods of modular forms. But in this joint work, we first consider some special case coming from the hypergeometric data defined over Q, and we give the answer for those cases. So first step is to identify the hypergeometric data coming from this Whipple formula. Okay, so the first step, let's look at the data here, the parameters here. So again, like the second column, the red part is actually defined by integer, like the Monotone subtle series example. So we will strike out the second column. Okay. And when we mark the P, the purple P part disappears. So which means the hypergeometric data we are considering is actually coming from a 6F5, like this, Okay, I remove the second column and the P part. Okay, and for the right hand side, we consider this hypergeometric data coming from this 4F3 function. Okay. So okay. In conclusion, we are considering the hypergeometric data coming from first a pair coming from the left hand side, the 7F6, and the second pair coming from the 4F3 on the right hand side. Okay, so and again in this joint work we consider all the data which are defined over Q. So there are only 7 pairs of them. Okay, so these are the only pairs. Okay, and okay, here I state a simple version of the result. So, but I will give a precise statement in the end of this talk. Here is just to give you some picture what the representation looks like. So, okay, so first, according to Katz, Boyker's, Cohen, and Mallet. So again, I will call it BCN to refer to their work. Okay, so from Katz and the BCN, we know that for these 7 pairs, and for the given hypergeometric data coming from the 6F5, so there is an elated Galois representation which can be extended to GQ, and it's a dimension 5. So, and we will use, okay, sorry. So in this joint work, we use the identities between hypergeometric correlations to further decompose the representation into 3 pieces: dimension 2, dimension 2, and dimension 1. So now we use the modularity of the 2-dimensional Galois representations, then we can theoretically verify that the representations are modular. Okay, so then again we use the data, we compute the hypergeometric correlations value, and also use the sales theorem to help us to identify the corresponding Hecke eigenform. So here is the list. So okay, so the label here is actually the label from the arrow function module form database. So for example, for CF equal to 1/2 case, so the trace of forbiddiness of the Galois representation are expressed in terms of level 8 wave 6 module form, and also another one is level 8 waveform module form and plus some p-squared terms. And for 1/3 and 1/3 case, they are expressed in terms of level 4 wave 6 module form and level 12 waveform module form, and some other p-squared terms, and yeah. Okay, so here I want to say a few words about the hypergeometric values. So actually we can relate the 7F6 value and the 6F1 value to periods of these 2 module forms. So as from the Whipple formula, we know that this guy is corresponding to the 4F3 functions in our Whipple formula, and this part is actually given by the Galois as we see in the previous example. So okay, so the 4F3 value is the period of this waveform module form, and as expected from the Whipple formula, so the 7F6 is also related to this waveform module form. And we can also show that the 6F5 value is the period of the wave 6 module form in the table. Okay, so so the path here is actually the hyperbolic geodesic connecting these 2 points, and the direction is counterclockwise direction. I will show you the peak in a few minutes. But before that, let me say a few words about the supercongruence part. So actually, this one is can be viewed as the Archimedean version of the supercongruence given by Osborne, Straub, and Rudling. Okay. So they show the truncated 6F5 is congruent to the Fourier coefficient of the wave 6 module form marked p cubed. And numerical data suggests that this supercongruence holds when marked p to a 5, which is sharp. So in the joint work, we list some other supercongruence conjectures related to these 7 pairs. So if you are interested in, please, you can take a look. But I will skip the formulas here. Yeah. Okay. So this is about the complex period and the periodic period part. So before I talk about the Galois representation, so I will give you some of the key idea how we obtain this identity. So the key point is that following Zagier, we rewrite this 6f5 in terms of this integral using residue theorem. So again, if we plug in t as by this module function, so then we have a way2 form here and another way2 form here, and this part is also way2 form. So this integral is actually the integral way6 form along the closed path t equal to 1. So now we have to figure out what's the path here. We look at the value. So actually, it's a homogeneous has a simple 0 on the cusp infinity, and the simple pole at the cusp 0, and take values 1 at the derivative point, this one. Okay, so this loop, sorry, this closed loop is actually the path, the geodesic connected these 2 vertices. So this one is equivalent to this derivative point of order 2. Yeah. So once we figure out the path, then again from the module forms that, as I mentioned in the previous example, then we can end up the identity like this. So for 7f6, we use the similar idea, but it's a little bit more complicated. So I will skip the detail here. Okay. Now it's about time to talk about the Galois representation. So before I proceed, any questions? No? Okay. Okay, in literature, actually, there are different versions of hypergeometric functions over finite fields, given by Katz, Green, and also McCarthy and the BCN the HQ functions that I introduced in my previous talk. So, but here I was starting from the version related similar to Green. Okay, so first we start with the integral representation of the classical 2f1 function. So from the binomial theorem, we can write the power series in terms of the integral here. So for convenience, I will let this integral to be 2p1, which I will call it the period function. Okay, so now if we look at the blue part, okay, and if we fix the exponent b minus 1, so when x varies, so actually this guy gives us a multiplicative function. So in finite field setting, our candidate will be a multiplicative character. Okay, so sums it up. So so again we will put denote the FQ hat to, we will use notation FQ hat to denote the group of the multiplicative characters on the finite field. And also here we will extend our character to be defined over in time. Sorry, to be defined on entire FQ by setting Chi-0 to 0, and denote chi bar the complex conjugation of the character chi, and it is its inverse because the character value are all root of unity. Okay. All right. So we define the finite field 2p1 function in this way. So here we replace the integral by the discrete integral. Okay. the summation. And also, again, we replace all the little ABC, the parameters, by our multiplicative character, capital A, B, C. So this guy, the Bx, is the finite field of the x to the b minus 1. Okay. So one thing I want to point out is that the trivial character, okay, is the finite field L log of the 1 here. So the CB bar is exactly for this part C minus B minus 1 and so on. Yeah, so back to our Legendre curve case. So in our notation now is that, okay, the 2B1 is the period of the Legendre curve, and the finite field 2B1 is give us the trace of covariance. So you can see here, the phi, again, the quadratic character is the finite field L log of 1/2, the half of integer. And the epsilon here, the trivial character, is the finite field L log of the integer 1 here. So they are exactly the same thing. Okay. All right. Okay, so this, so we now we have one function. What? Oh, okay. So we can define a higher dimensional P function inductively by this formula, which is parallel to the classic, parallel to the integral representative of the classical hypergeometric functions. Yeah, and when lambda is not equal to 0, using the finite field version of a binomial theorem, we can rewrite this P function in terms of finite field binomial coefficients, okay, which is a normalized Jacobi sum, okay, like this. So we can, yeah, so we can express the P function in terms of Jacobi sum and Gauss sums as well. So yeah, so this is a finite field version of a period function. So for the hypergeometric functions, we will do some normalization, which is parallel to the classical case. So, okay, so as gamma function, sorry, Gauss sum and the Jacobi sum are finite field of the gamma function and the beta integral. So here we do a normalization like this, then we get the finite field 2f1 function. Okay, so in this case, so for this case, when lambda equal to 0, the 2f1 function, the value gives us the 1, which is the same as the classical 2f1 function. Okay. Right. So, and we can define the higher dimensional hypergeometric function over finite field in a similar way, but I skip the definition here. Oh, okay, so about the Galois representation, again, we need something else. So first, we have for given multi-set alpha and beta, and we consider the finite field FQ, whose characteristic is applied to this common denominator of all parameters. And also we will require Q to be the number Q congruent to 1 when mod M. Okay, so this is to ensure that the numbers Q minus 1 times AI are integers, and so are Q minus 1 times BJ. And again, we will fix a generator of the multiplicative group, and then once we fix the generator, then we just take capital, the character capital AI to be the character arising from the little AI, and so is capital BJ. So, and for shorthand, we use the notation P alpha beta lambda and Q to denote the period function defined over FQ. Yeah. And in this talk, for convenience, I will use FBCN to denote the HQ functions that introduced by BCN. Yeah, so actually, they are equivalent to the hypergeometric function over finite field that I that defined in a previous page. Yeah. Okay. So yeah. So why I mentioned this two is first, if I because it's kind of easier to find the useful identities between P functions parallel to the classical case, but we would use the BCN's hypergeometric function to extend the representation to GQ. Yeah. Okay. So let me recall the definition about BCN's HQ function. So yeah. Okay. So BCN's HQ function is defined in terms of Gauss sums, okay, which is finite field analog of the f function, the classical f function, when we write the coefficient in terms of the gamma function like this, right? And okay, so when the hypergeometric data is defined over Q, then actually BCN gives a recipe to construct an algebraic varieties arising from some toric model, and they show that the data function of this variety can be computed using HQ functions, which works for all FQ without the restriction here. Yeah. So for example, okay, again, another example that I also mentioned in previous talk, but if we consider the Elliptic curve, so which is corresponding to the hypergeometric data 1/3, 2/3, and 1/1 here. So the trace of Frobenius of this elliptic curve can be given by these HP functions, which is defined in this way by applying the multiplication formula of the Gauss sums. So we can get rid of the order 3 character here, and this works for all prime P. Okay. So, and BCN tells us, okay, this one is the correct one to give us the Galois representation. Okay. Any questions? No? Okay. Galois representations. So anyway, the first few lines are some set out, but the key point is that we will have a Galois representation, and which can be computed using the P function, the F function. So, okay, this is a result from CAT and the BCN. So if we have multi-set alpha, beta, then we get, so first we pick out what's this LCD of all the parameters M, then we consider the absolute group of the cyclotomic field. And now let lambda to be a non-zero element in this ring. So for this hypergeometric data, for a prime L, there is a L-adic and L-adic Galois representation. Yeah, and the trace of Frobenius of this Galois representation is basically is equal to P function evaluated at 1 over lambda and pluses, and there are they differ by some plus or minus sign here, okay, depending on the A1 here. Also, the trace is equal to, we can also use BCN's HQ function to compute the trace, and they will differ by some power of the cardinalities of the residue field, and also another part coming from a character of the Galois group. Okay, but here the exponent and this chi can be explicitly determined depending on the hypergeometric data that I skip the description here. Yeah. So now we have a Galois representation, and what's the dimension? So for generic lambda, the dimension is equal to the length of the multi-set alpha. Okay, so when lambda equal to 1, the singularity of the differential equation, so we have one dimension drop. So this is a degenerate case. And especially if the data is self-dual, then so we have a representation print, which has a dimension this guy. Okay, right. Okay. So and if the HD is defined over Q, so according to PCM, this representation can be extended to GQ. Okay, and the trace of Frobenius of this representation again it can be computed using the BCN's HQ functions. And okay, so for all prime, which is coprime to m times L. Okay, so this gives us some idea to compute the. So now we have the Galois representation, and we know how to compute the trace of Frobenius. Okay, so for example, the example came from our Calabi-Yau threefold case. So if we consider the hypergeometric data 1/2, 1/2, 1/3, 2/3, and beta is 1. Okay, so in this case, the length is n equal to 4, lambda equal to 1. So it's a degenerate case. So in this, okay, so we have a degree 3 Galois representation, and because this HD is defined over Q, so the representation can be extended to GQ. Okay, right. And again, because this HD is self-dual, so we have a prime part of the representation, which is dimension 2. And actually, this Galois representation decomposed in 2 parts, 2 + 1 representations. And as we see in previous talks, we know that this prime part is modular, and we can identify the corresponding waveform form like here. Okay, so the trace of Frobenius of this Galois representation is actually equal to the BCN's HQ function, HP function. Okay, and equal to the P part plus some Fourier coefficient of this waveform form. Okay, yeah. So this, and also this part is the 4F3 corresponding to the 4F3 in our Whipple formula. So what's the left-hand side? So the left-hand side is this hypergeometric data, which corresponding to the pair CF equal to 1/2 and 1/3. So from KBCN's result, we know, okay, we have a degree 5 Galois representation, which can be lifted to GQ. And also this is self-dual, so we have a prime part whose dimension is 4. So now the question here is that whether we can relate this prime part to the, okay, the prime part for the 4F3 function, like this, as expected in a classical Whipple formula. So, and also we want to know whether it is modular as expected. Okay. So to answer this question, okay, roughly speaking, by the fact that a semi-simple Galois representation is completely determined by the data of the trace of Frobenius, so which reduced to consider the finite field version of the Whipple formula. So once we, okay, so this is a classical Whipple formula. So now our goal is to try to relate the Whipple formula, the 6F5 here for finite field version to this 4F3. Okay, in the classical Whipple formula. So now we consider the finite field version of the evaluation of this 6F5. So again, we would let phi to be the quadratic character, which is a finite field analog of the half integer here, 1/2 and 3/3 here. Sorry, 3/2. So we replace 1/2 integer by the quadratic character phi. And also we let epsilon to be the trivial character. So which is a finite L. It is the finite field analog of the integers 1, 1, 1 here. Okay. So and for the little c and f, we replace by the capital we replace it by multiplicative character CM and F here. So now the goal is to find what's the evaluation for the finite field version of Whipple formula to relate this guy to the finite field version of 4f3. Okay, but we tried the different versions, but it turns out if we shuffle the low parameters a little bit, then we get an identity like this, which is sum over all the fiber from a square of 3p2 and the sum twist. Okay, still we don't see a 4f3 here, but why this is useful because we can use the finite field version of a Carlson formula to break this 3f2. Then we get a square of 2f1. Then we can from there we can create a 4f3. Okay, so back to our example. Yeah, again we let the CF to 1/2 and 1/3. So this is the identity from our finite field version Whipple formula. Okay, so as I mentioned here, so this 3f2, we will break this 3f2 into a square of 2f1 plus some error terms, okay, by the Carlson formula. Okay, so now we have a square of 2p1. Okay, okay, and another part which is equal, which is at t equal to 1 case. Okay, so the first line here is the square. So we expand the square, the complete square here. So we have square part, mixed terms, and the square of p part. And for the mixed terms here, actually, it follow the definition of p functions, then we get a 4f3. So now, and again, we have some leftover from the 3p2 here. So, okay, so again, by the Carlson formula, we know that the evaluation of this 3p2 can be expressed in terms of Jacobi sum. So, okay, in terms of Galois implementation, they can be expressed in terms of Gaussian character or so-called Hecke character. Yeah, and for the purple part, 4f3, okay, this is the same as the Calabi-Yau threefold case. So actually, okay, in terms of the numbers, rational numbers, this is the 4f3. So from earlier example, we know the exactly corresponding way for eigenform. But now for this 4p3, we have two candidates, either level 12 or level 36. Okay. And yeah, once we pick up this 4p3, then we can identify the value for the 6p5 and the other V6 module form here. So this is kind of, roughly speaking, this is kind of the idea how we identify the corresponding Hecke eigenforms. Yeah, but again, like I said before, for the p function, we have some restriction. So for example, in this case, the p should be congruent to 1 mod 6. So for the other help prime numbers, how to deal with that, then we will use BCN's idea. So again, so for the 4p3 function, if we write this in terms of Gauss sums, then we apply the multiplication formula of Gauss sums, then we can get rid of the other three characters. So it's like this. And the BCN tells you that, okay, this guy is exactly the one that we want. So now using the formula, which means the BCN's SQ functions, then we can identify the waveform module form corresponding to this 4p3. And so similarly, we can identify the V6 module forms for all the prime numbers, for all prime numbers greater than 5. Yeah, so this is the idea. Okay. So, okay, from this example, we see here, actually, besides the first two hypergeometric data, we need another one coming from the 3p2 in my Whipple formula. Okay, so now, okay, So for this 3p2, again, we can use the finite field version of the finite field version of the Gaussian formula to break down the 3p2 in terms of 2p1. So here I write the version which is a 2p1, the product of a 2p1 and its complex conjugation. Yeah, and when t equal to 1, this value can be expressed in terms of Jacobi sum like this. So this kind of gives us the idea how to decompose the Galois representation. Okay, so in terms of Galois sum's identity, so let's look at the representation coming from the 3p2. So for this hypergeometric data corresponding to 3p2. So again, these are some setup. So we have some degree 3 or degree 2 representation associated to this hypergeometric data. Okay. I want to point out that the additional capital N here is actually, so these two guys are coming from the 2p1 here. Okay, yeah, so coming from the Gaussian formula. So anyway, so after we set the capital M and capital N, then we have the Galois representation. Yeah, and the trace is equal to the P function and times a quadratic character evaluated at -1, right? And from here we talk about the alternating square and the tensor product. Okay, so the trace of the alternating square of this representation is equal to the 3p2 function with some twist. Okay, and for the symmetry square, so it's coming from the tensor product remove the alternating square. So this is the formula for the trace of the symmetry square. So coming from the square of 3p2 and the other part from the alternating square. Okay, so from the formula, actually this is corresponding to 4p3, and this guy, the square here, corresponding to the 6p5. So from this, so putting all together, which give us the information on the Galois representation, right? Okay, so back to our statement. The Galois representation associated to the first hypergeometric data, okay, corresponding to the 6p5 in the Whipple formula. So we have a Galois representation, this one, and when restrict on this Galois group, it is isomorphic to the direct sum of a two-dimensional representation, and then the other part is coming from the tensor product of the analytic cyclotomic character and the representation coming from the second pair, which is related to 4p3. 4f3 in the Whipple formula. So this part. So actually the red part is this red part here. And again, yeah, you can see here it's really parallel to the Casio case because this one we consider, so this cyclotomic character is corresponding to P part here. The trace of the Frobenius of this row is corresponding to the 4f3 here. So this is kind of different. If the finite field, sorry, not finite field, the Galois representation version of the Whipple formula. Yeah, and thank you very much. I will start here. Yeah. Okay.
Yeah, thank you, Professor Ting too for this interesting talk. And I mean, really interesting to see the Galois representation side associated to hypergeometric functions. So I mean, this work is already available. I mean, published or?
Yes, it is available. Yeah, I forgot to give the journal. Yeah, but I will add the reference.
Okay.
I posted the slides.
Are there any questions from the audience?
Well, may ask a couple of questions here?
Yeah, please go ahead.
There are two things in this work that are really mysterious to me. Let me start with your formula for the, I guess it was the, I can't remember, it was the 6F5 as a sum of phi of, yeah.
Wait, here, wait,
Yeah.
this one, okay.
Yeah. I don't understand that formula. I mean, see, I try to think geometrically in terms of geometry, and these represent cohomologies of varieties. And what you have on the right-hand side seems to be like you have a fiber space. Do you have any interpretation of that formula geometrically?
So
I don't have the.
That's the Zargate's formula written in the finite field form.
Yeah, I agree, but I'm not asking that. I agree the formula is correct. I'm asking what's
And the
geometry?
geometric is the current work we're joining with you. And this is the, yeah.
Okay, well,
The
we'll
generalization is in our current joint paper with you. Yeah.
Okay.
It's just a special example. Maybe it's not easy to be recognized in terms of algebraic geometry right now.
Well, thank you, Ling. Well, now let me tell you the second thing that just blows my mind, and I do not understand. It's your period of those Eichler integrals. Now, I've never seen anything like this in my life. I'm somewhat familiar with Eichler integrals, but usually they're what are called modular symbols. Now, I guess in your example, it was a gamma of 2, gamma naught of 2. What was, I don't remember.
Like this.
Yeah, right there. Now, so to me, modular symbols are integrals between cusps.
Yeah,
And
but
here,
that's vocab.
I'm not
Okay.
disputing the form. I'm not disputing the formula. But what I'm asking is, what the heck does it mean? You're integrating between elliptic points.
Yeah.
It is
Can
a
you
closed
explain?
loop. Yeah. Anyway,
It is a what?
It's a
A
closed
closed
loop.
loop.
From cusp
Like
to
T.
cusp, it's a closed loop. This is another
I
closed
know
loop.
it's a closed loop, yes. I'm not disputing that either. I'm thinking in terms of Eichler periods in general, okay? And my limited understanding of these things, the theory of modular symbols, is usually these are geodesic arcs between cusps. And this is the first time in my life I've seen Eichler periods between elliptic points. And I've never seen anything like this. And yet they're coming up in the evaluation of these L functions. And I think that's mind-blowing.
To us, I think the question is why not?
Oh, come on. Well,
Yeah, I think it's just when we go to the Schumann curve case, then we don't have any customers anymore. So yeah, so one of the canonical choice is for the elliptic curve. Sorry, it's from the elliptic point. And if my memory serves well, I think John Lloyd also discussed some computation using the elliptic point to compute the module symbol for general case.
Yeah. So this is an aspect of this work that I think is fascinating, because these are some kind of Eichler periods that I've never seen before showing up in the valuation of these L functions. And I find that extremely interesting.
Thank you.
Indeed.
Any more questions? I think there is no more questions. Then let us thank Professor Fang once again for this interesting talk. Yeah.
And thank you for
Thanks to
Thank
Professor
you for
Barman
your
for
joining
sharing
us.
also. And
What?
I'm thanking Professor Barman for sharing this talk also, and
Thank
Oh,
you.
yeah.
again
Thank
next
you.
week.
It's my pleasure.
So you will
Okay.
be sharing next week Fang of talk of
Yeah.
Professor Fanyan. So see you
Okay.
next week again. Bye.
Okay, see you. Okay, bye.
Bye.
Bye. Bye. Okay.
Pawan, you can stop the meetings and everything.
Okay.